everyone, this is Kalpana here. In this video, we are going to see a problem from Mathematical Induction. So let's get started. Problem. Using the Mathematical Induction, show that for any integer n greater than equals to 2, 3n square is greater than n plus 1 whole square. So here we have to show that this statement is true for any integer n greater than equals to 2. N greater than equals to 2 is nothing but for n equals to 2, 3, 4, 5 and so on. Okay. We are given equals to, so that we'll consider 2 also. Fine. Okay. For integers. Let P of n be the given statement. Then P of n such that 3n square greater than n plus 1 whole square with n greater than equals to 2. Okay. So here we'll show that the statement is true for n equals to 2, and we'll assume that the statement is true for some n equals to k, and we'll prove the statement is true for k plus 1, that is for n equals to k plus 1. When n equals to 2, since we are given for any integer n greater than equals to 2, so that will prove firstly for n equals to 2. Okay, since n starts from 2, so that we are taking the first number 2. Okay, fine. Now consider 3n square. Now put n equals to 2. You'll get 3 into 2 square is 4. 3 4s are 12. Now consider the RHS part. N plus 1 whole square. Put n equals to 2. Then you'll get 2 plus 1 3 square, which is equals to 9. It is clear that 12 is greater than 9. Therefore, 12 is greater than 9. Okay. Since LHS is greater than RHS, so from this we can say that therefore P of n is true for n equals to 2. There's nothing but P of 2 is true. Okay. Likewise, you can check it for n equals to 3. Okay, fine. Let's see what happens. We put n equals to 3. LHS. 3n square equals to 3. You're having n equals to 3. So you'll get 3 into 3 square is 9. 3 9s are 27. Now coming to RHS. N plus 1 whole square. Now put n equals to 3 in the RHS. You'll get 3 plus 1 whole square equals to 3 plus 1 is 4 whole square. 4 square is 16. It's clear that 27 is greater than 16, right? Number 27 is greater than 16. So here also LHS is greater than RHS. So from this we can say that the statement is true, that is P of n is true for n equals to 3. Therefore, P of 3 is true. Okay, fine. Likewise, you can check for n equals to 4, 5, 6, any number for n greater than or equals to 2. Right. Now assume that P of n is true for some k. Okay, that is for n equals to k, I can say. Then P of k will be 3k square greater than k plus 1 whole square. Okay, so here we have 3k square is greater than 3 plus 1 whole square. This is true. We are assuming that the statement is true for n equals to k. So we can use it. Okay. Now we'll prove for P of k plus 1, which is equals to, consider LHS part for n equals to k plus 1. Okay. This is equals to expand k plus 1 whole square, that is k square plus 1 square plus 2 into k into 1. That is equals to 3k square plus 3 into 1 square is 1, 3 plus 3 2s are 6 into k into 1 is 6k. Okay. Since 3k square is greater than k plus 1 whole square, since 3k square is greater than k plus 1 whole square, then this must be greater than k plus 1 whole square. Okay, this must be greater than k plus 1 whole square plus 3 plus 6k. 3 plus 6k. Since 3k square is greater than k plus 1 whole square. Okay, we are simply taking this 3k square is greater than k plus 1 whole square, and remaining will be as it is. Okay, don't get confused. Okay, if you want you can check. See, this is the statement, right? We have used. So let's put k equals to 1 or 2 better. 3 into 2 square plus 3 plus 6 into 2 is 3 4s are 12 plus 3 plus 6 2s are 12. So 12 plus 12 is 24 plus 3 is 27. Okay, 24 plus 3 is 27. Right? So this is equals to 27. Now coming to RHS, put k equals to 2. Then we'll get 2 plus 1 whole square plus 3 plus 6 into 2, which is equals to 2 plus 1, 3. 3 square is 9 plus 3 plus 6 2s are 12. 12 plus 9 plus 3 is again 12. So 12 plus 12 is 24. Okay. See, it's clear that 27 is greater than 24. Right? So this statement is correct. Whenever you get doubt, simply substitute some number to that k according to the given condition or given hypothesis, I can say. Okay, so we have this is greater than, right? So this expression, okay, leave this greater than symbol. This expression is equals to expand k plus 1 whole square, that is k square plus 1 square is 1 plus 2k plus 3 plus 6k, which is equals to k square plus 2k plus 6k is 8k plus 1 plus 3 is 4. Right? Again, you can split this as k square plus you're having 4, right? So write firstly 4 and you're having 8k. So you can split this 8k as 4k plus 4k. So this is equals to k square plus, you can write this 4 as 2 square plus, you can write this 4k as 2 into k plus 4k as it is. This is of a square plus b square plus 2ab form, right? So you can write this as, the total expression as k plus 2 whole square plus the last term as it is. So this expression is equals to k plus 2 whole square plus 4k. Okay, we are simply simplifying this. Okay, fine. Now you can write this as k plus, you can split this to as 1 plus 1 whole square plus 4k. Simply we are writing in terms of k plus 1. So you can write this as k plus 1 whole square plus 4k. Okay, here we are writing in terms of k plus 1. Don't get confused, okay? We are writing in terms of k plus 1. Okay. In order to prove the statement, the given statement is true for n equals to k plus 1. Right? Fine. So we are having k plus 1 whole square plus 4k square. Can we say that k plus 1 whole square plus 4k is greater than k plus 1 whole square? See, we are having same term in LHS and RHS, but in the LHS you are having one more term, that is plus 4k. Okay, which means that this term, this expression is greater than this expression, right? If you want, you can check it. 4k equals to some 2 plus 1 whole square plus 4 into 2 will be 2 plus 1 is 3 plus 1 4 square is 16 plus 4 2s are 8, 16 plus 8 is 24, right? Now coming to RHS, put k equals to 2. This is equals to 2 plus 1 3 plus 1 4 square is 16. So it's clear that 24 is greater than 16, which is nothing but this expression is greater than k plus 1 whole square. Okay? RHS for n equals to k plus 1. K plus 1, that is n plus 1 whole square. So from this we can say that therefore P of k plus 1 such that k plus 1 3 times k plus 1 whole square LHS is greater than RHS. Okay, that is, the statement is true. This statement is true for n equals to k plus 1. See, 3n square, we got 3n square greater than n plus 1. Okay, we'll show it again. 3n square greater than n plus 1 whole square, right? Therefore, P of n is true whenever P of k plus 1, okay? P of k plus 1 is true whenever P of k is true. We have used P of k condition to prove that P of k plus 1 is true. Okay, so we can show that P of k plus 1 is true only whenever P of k is true. Okay, if P of k is possible, then only P of k plus 1 will be possible. Alright. So from this we can say that P of n is true for n equals to k plus 1. Okay. So one more condition here, k must not be equals to minus 1. Minus 1 or 0. So let's see what happens if put n equals to, k equals to 0. I'll take LHS part. 3 into 0 plus 1 whole square equals to 3 into 0 plus 1 is 1 equals to 3. When k equals to 0 in the RHS, 0 plus 1 whole square equals to 2 square equals to 4. Is 3 greater than 4? No, 3 is less than 4, right? So this is not possible when k is equals to 0, right? So what happens when we put k equals to minus 1? When k equals to minus 1, consider LHS. 3 times k plus 1 whole square equals to 3 times, put k equals to minus 1, then we'll get 3 times. Minus 1 plus 1 is 0. 3 into 0 is 0, right? Now coming to RHS, put k equals to minus 1, you'll get minus 1 plus 1 whole square is equals to minus 1 plus 1 is 0. 1 square is 1. Is 0 greater than 1? No. 0 is less than 1. So here we can say that this is not possible when k equals to minus 1, right? So from this we can say that the statement, that is this one, is true when k is greater than 0. Okay. For k equals to 1, 3 into 1 plus 1 whole square equals to 3 into 2 square equals to 3 into 4 is 12. Check for RHS. Equals to 1 plus 1, 2 plus 1 whole square. 2 plus 1 is 3. 3 square is 9. It's clear that 12 is greater than 9. Okay. So the statement satisfies when k equals to 1. Right? Fine. Okay. So therefore, P of n is true for n equals to k plus 1. Right? Thus, P of 2 is true and P of k plus 1 is true whenever P of k is true. Therefore, by the principle of mathematical induction, the given statement is true. For any integer n greater than or equal to 2. So this completes the problem. So we have seen a problem from mathematical induction in this video. You'll understand. We'll see you in the next video. Until then, bye bye.